Hello, my name is Bezawit Haile and I'm a PhD candidate at the University of Toronto. Today I'm going to present to you one of the primary research projects I've been conducting for the past few years here at the University of Toronto and under Professor Grissel's geomechanics group. My main research topic focuses on understanding the tensile fracturing and mode 1 fracture energy of rocks, more specifically sedimentary rocks like mountain shale and granitic rocks like sandstone granite. So if we look at the background of this research, understanding mode 1 fracturing and tensile strength of rocks has many applications in the energy sector, including oil and gas, geothermal, and mining. For hydraulic fracturing, it helps to determine the fracturing pressure, helps to design the optimal way in which cracks extend to maximize reservoir connectivity and production. It also influences drilling efficiency, drill bit selection, and well design. In energy infrastructure construction, such as tunnels for hydropower stations, it helps assess the collapse risk and guide reinforcement. In addition, this knowledge is key for maintaining reservoir integrity and preventing unwanted fracturing. Hence, laboratory investigation of this rock mechanics property is very critical. Next, if we move on to the purpose of the study, in the study to experimentally quantify mode 1 fracture energy of rocks, a stiff tensile testing setup was designed and built in-house to allow for the measurement of fracture energy of rocks directly from the direct tensile test. Obtaining the accurate post-peak curve of rocks failing in pure mode 1 fracture allows us to accurately quantify the true tensile strength and fracture energy of the rocks. The post-peak curve can then be used for numerically modeling the fracturing properties of these rocks. In conventional rock mechanics laboratories, Brazilian disc test and the 3-point bending experiments are used to determine the indirect tensile strength of the rocks, while notched bending experiments are used to determine the fracture toughness, which is then used to calculate the fracture energy of the rocks. In this study, we conducted all three types of tests to compare and highlight the variation in the tensile fracturing properties due to mode of testing on sandstone granite and mountainy shale rock. Next, if we look in depth into the research methodology used for this study, the experimental investigation involved working on shale and granite samples with dog bones samples and notched and unnotched 3-point bending samples and BD samples. The dog bone shape for the direct tensile samples was made using the Tormax CNC mill, and the beam samples and the BD samples were cut and surface ground to have flat and parallel surfaces. This is the in-house built direct tensile testing setup that we have, and the first one is the CATIA design and the final built testing frame. High-speed camera imaging with up to 120,000 frames per second was used to capture the post-peak curve during fracture propagation in the direct tensile test and 3-point bending test, while regular DIC 5 to 20 frames per second was used to capture the surface displacement of the full test. The final results we have obtained so far are as follows. From the three types of experiments, significant differences were observed in the tensile strength, measured fracture energy, and generated fracture surface of the rocks. While the direct tensile and 3-point bending generated clear single fracture planes, the BD seemed to show significant damage to the rock with branching cracks observed, which can be attributed to the existence of bimodal stress state, which is compression as well as tensile. Next, if we look at, now moving out again, we can see the mountain shale showed larger tensile stress than granitic rocks, which has interesting applications. In addition, as can be seen in the right image here, we were able to obtain the post-peak curve for some shale and granite samples using the high-speed camera DIC analysis and calculated the fracture energy from this post-peak curve. Next, if we explore the tensile strength of shale rocks based on bedding plane orientation and testing method, we can see that there is a huge variation in the tensile strength obtained by mode of testing. The trend also seems to indicate different values for bedding plane orientation, which does not match in all of modes of testing. Next, if we look at the fracture energy values obtained for different tests, the fracture energy comparisons of the direct tensile test were made with notched beam samples, and as can be seen in the figure, the results from the 3-point bend samples showed significant variation by sample size, which can be attributed to the 3-point bending being highly susceptible to side effect. In addition, the fracture energy values are much higher than the fracture energy values from the direct tension. High fracture energy values implies the rock is tough, resistant to crack growth, and requires more energy to fill. This is beneficial for stability, but problematic for excavation, blasting, and hydraulic fracturing efficiency. However, this variation in the values of fracture energy can lead to overestimation of the rock's actual toughness due to mode of testing, creating potentially dangerous and expensive real-world implications. Finally, this research is ongoing, and we're trying to draw conclusions on which mode of testing we recommend to obtain testing method independent fracture energy that can be used for numerical models and real-world applications. With that, I would like to conclude my poster presentation and thank you for your attention. Please come visit my poster at the Energy Simulation Summit 2025 in Rio for better discussion on our interesting work. Thank you.